Okay, well, here it is. This is my purely symbolic expression of partial fraction decomposition, and as you can see, I can basically express it in 1, 2, 3 main steps. And I'll explain what this is, what this all means shortly. And the key thing here is that it works, so this input here, this right here, can be literally the most general fraction. So we literally have any general polynomial c of x divided by any general polynomial b of x. Doesn't matter if it's proper, improper, although I should note that the way I formulate it here is quite symbolic, maybe a bit too symbolic for some people. It's quite theoretical, I suppose, but the thing, and when I first came across partial fraction decomposition, I was really confused and really frustrated that there wasn't one unified method where you could just follow an algorithm, bish, bash, bosh, and then you're done. And it always works, and you can always find out the template for any fraction like this. So that's what I'm supposed to do in this video. And when it comes to maths, I feel like there's always room for, sharing new ideas and new ways of thinking about things. And so this is sort of like how this, and thinking about it like this is sort of what helped me understand partial fraction decomposition. So there we are. It's just a nice little algorithm you can follow. So I'm going to build up to this, so let's get started. The way they usually teach this topic is they start off with a really simple case, something like this. And then they say that this can be expressed in this sort of form. And that's fine. That's pretty easy. But that's only because this is a pretty special case. And then the way they usually teach this is that they start branching off into more difficult cases, and then they're like, oh, what if we have x plus 4, and then we have x plus 2, and then what if we have a irreducible quadratic here? And then they're like, oh, in this case you have to do this. Right? In this case, it's going to be like this. And so on, and it just gets really confusing. So they usually start with a simple case, and then they're like, oh, but if there's this, then you have to do this. And then, I don't know, this just doesn't really work in my brain. So this took me a while to actually understand. And I think the way that worked for me is I start off by thinking about the most general case. And then, so in this video, I won't be going over like the intuition behind all this that much. I just want to pass my A-levels, okay? That's all I care about. I just want to make an algorithm such that you get the correct template every single time, and I don't want it to go around it in a really roundabout way, where it's like, oh, but if there's this, then you have to do this. Just sequence of instructions, and you always get the right template. So maybe this will be helpful if you're making like a computer program to do this or something. So I'm going to start off by defining some notation, and I'm going to start with the most general case, rather than starting with a special case, which just gets confusing, because you have to unlearn what you learnt every time you go to a more difficult case. So that just doesn't work for me. So let's just, for the sake of notation, let's define a function t, and let's say we have a subscript k of x. So this is a function in terms of x. This t is supposed to stand for template, right? And basically what this is going to be defined as is pick a variable name, so like a, b, c, whatever, has not been used before. In this case, I'm going to pick a. So this function is basically going to be giving you a template for a polynomial of order k. So this might look like this: a0 x to the 0 plus a1 x to the 1 plus a2 x to the 2 all the way up to a, let's say k minus 1 x to the k minus 1 plus a k x to the k. So that's like the general form of polynomial, and maybe you can write it like this if you want to. R equals 0 up to k a r x to the r. So that's basically the same as that, okay? And what I mean by this is, so this is basically going to be this top thing here. Notice how we used a here, now we use bx plus c. So to explain what I mean by this, let's just go for an example. So let's say we want a template of polynomial with order 2 in terms of x. So this might look something like a 0, well, x to the 0 is just 1, so it's just going to be a0 plus a1, x to the 1 is just 1, plus a2x squared. See, so there we have a template. And what I meant with this thing is, if we want to define another template, let's say we have a cubic this time in terms of x, then I don't want to use a again because I've already used that. So let's use b. That's basically what I'm saying. And in this case, it will be like this. So yeah, that's just like a notation, because I don't want to write out this every time in the general case. So now we can start generally defining partial fraction decomposition. Okay, now with t, the function t properly defined, which is basically our template function, although it is a bit not very rigorously defined, I suppose, with this thing, but whatever, you get what I mean. Anyway, so now we can move on to the algorithm. So hopefully this should be the most general algorithm which should work, so which if you follow, you should be able to do the partial fraction decomposition of literally the most general. So let's say we have something like this. Literally the most general fraction. So we have a polynomial up top and a polynomial down bottom. In the general case, this should work whether this is a improper or a proper fraction. So whether this has a higher order than b, so whether degree of c is higher than b, that of b, or the degree of b is higher than that of c. So our first step is, if it's an improper fraction, i.e. the degree of c is higher than the degree of b, then our first step is to do polynomial division, because we want to make it a proper fraction. So polynomial division, basically we get cx, we divide by b of x, and then we do, blah blah blah, whatever, and then we're going to end up with some remainder here and some quotient here. Get some quotient and a remainder. So we can write this as q of x plus r of x over b of x. And now the key thing is that the degree of this will always be lower than the degree of the denominator here. So this is always going to be a proper fraction. And if we started with a proper fraction anyway already here, we don't need to do this step. And in that case, this q of x will essentially become 0. But anyway, as you can see, this being a proper fraction is just a special case of this more general result. And when it's a proper fraction, this q of x can basically be thought of as 0, and we can continue the algorithm. So now we want to completely decompose this proper fraction as well, okay? So remember that this is a proper fraction. Now, the next step, what we want to do is we want to completely decompose this denominator polynomial into its factorized form. So completely factorize this, and in the most general case, this might look something like this. So we might have one factor here, polynomial 1 in terms of x, and all raised to the n1. And then we might have another factor like this, all raised to the n2, times p3 of x, all raised to the n3, times, and so on. So in the most general case, if we completely factorize this, if we completely factorize b, it'll look like this, in the most general case. So just to give a little concrete example, just in case I'm becoming a bit too symbolic here, so let's say this might look something like x plus 3, x plus 4 squared. Notice that this x plus 3 here is really x to the plus 3 all to the 1. And then we might have like x squared plus 4, and then x minus 2, something like this. Notice that we can actually decompose this further into complex numbers, like this, x plus 2i, x minus 2i, like this, but we don't want to go that far. We only want to decompose it such that we don't have i's. So we want to decompose this, so fully factorize this up until it's a form like this, and in general, the general way of writing that form might be something like this. Okay? Now I can explain how to partial fractionize this. So, we don't really care about this Rx because we want to make a template, right? So, let's start off by thinking about this one, okay? So what we do is we have P1 of x in the denominator here. And then we have a template of the order, which is degree of P1 of x, I suppose, minus 1, and this is in terms of x. Okay, this is quite symbolic, but hopefully at least like one person is like following along. So that's our first term. Notice how this is all to the 1. Okay, then we have t degree p1 of x, so minus 1. So the degree of this template is going to be 1 lower than the degree of the polynomial on the bottom there. X over p1x all squared plus t degree p1 of x. So degree is always going to be 1 less than the degree of that polynomial, p1. Just this inside bit, by the way. And then we're going to raise it to about 3. And then we're going to go all the way up, t degree p1 of x minus 1 in terms of x, all the way up to, all the way up to p1 of x, all the way up to n1, which is that n1 there. We're not done yet. Then we're going to consider this factor. So now we're going to do degree, a template of degree p2 of x minus 1 in terms of x. Then on the bottom we have p2 of x all to the 1 and all the way up to t degree p3. Oh wait, no, p2 minus 1 all the way up to n2. And so on. So maybe we can simplify our notation a bit here. Let's say that the phi of n is equal to, well actually, let's say that the phi of some polynomial p is equal to the degree of p of x minus 1. Yeah, that might simplify our notation a bit. So, in essence, this becomes t phi of p1 and so on. And we can simplify our notation a bit even more. So we can say, we can use sigma notation, and let's pick, I don't know, I equals 1 up to the number of polynomials we have. So we have P1, P2, P3 all the way up to, let's say we have all the way up to PM, all the way up to there, okay? So no of factors, irreducible factors in the denominator, okay? Want to do T of phi of Pi in terms of x divided by Pi, T phi of Pi x Pi of x all raised to the j. So in the most general case, the partial fraction decomposition of a general proper fraction is precisely this. It's very symbolic, might be a bit confusing, but I don't know, maybe this will help someone who is more symbolically inclined. Like maybe someone who doesn't really understand it too much when there are lots of cases and you do it in a lots of case-by-case basis, and they just want one unified system, although it is like obviously very symbolic and might look complicated. One unified system. There we go. So I don't know. There's always room for like different methods of doing things, maybe. And you know what? This actually kind of made sense to me. I don't know, my brain's kind of weird, but whatever. So now, with all that said, I can write my summary, and I can just summarize my formulation of partial fraction decomposition. Okay, so let's say we have some general polynomial divided by another general polynomial. Well, if we do polynomial division, we're going to have some quotient plus some remainder over bx. Okay, so this first step is polynomial division is the first step. Our next step is to fully factorize b of x. So now we can write this as r of x, and if we're using the capital Pi notation, then we're going from I equals to 1 up to m p of I, which is one of our irreducible polynomial factors, to the power ni. So like that. So this step is so we want to fully factorize bx into irreducible factors of the form p1 x to the whatever times p2 x to the whatever, and so on, all the way up to n. So there we go. And then the next step is to do the crucial, which is like the heart of it all, the actual partial fraction decomposition step. So we go from I equals 1 up to m, then we go from j equals 1 up to ni, ni, then we do t phi pi in terms of x divided by pi x all raised to the j. Okay, and now let me just quickly, I should probably see what this is. So this is our partial fraction decomposition step. And below here, let's just quickly define some of these terms. So I define phi of p to be the degree of p minus 1, where p is some polynomial. And let's just quickly define what I mean by t of k in terms of x, and t of k in terms of x is a template polynomial of order k in terms of x, i.e. t of k in terms of x can be formulated like so: r equals 0 up to k a of r x to the r, where this is not necessarily always a, it's just some placeholder, I guess template constant, like so. And so there we have it. It's my complete formulation, very symbolic formulation of partial fraction decomposition, and there we have it.